Welcome to a lesson with Dr. Powell. Let's take a look at an example of using L'Hopital's rule, um, where we have something like 1 to the infinity. At least the top is heading toward infinity and the bottom's heading toward, the base is heading toward 1. So the exponent toward infinity, the base toward 1. And the limit is not actually 1. Let's look at a case where it's actually e. So we can kind of see this difference. So as indicated in the last video, something like 1 to the infinity should be equivalent to the idea of like a 0 over 0, especially if you think just intuitively like this. Take a natural log and you get natural log of 1 over 1 infinity. This looks like a 0 over 0 situation. Now, a 0 over 0 situation or an infinity over infinity situation are just not well defined. I mean, in terms of like knowing what they are symbolically. For instance, what if we had 5x over x and we're taking the limit as x approaches 0 or infinity? Either one would be in either case. Notice what happens here. This limit is 5. Yet if we just change that 5 to 4, guess what the limit would be? It would be 4. So this tells us a set of situation of 0 over 0 could be 5 or 4 or anything, really. Same thing with infinity over infinity. It could be anything. So we have to do some limit work to see what these are. It's not enough to say you can't cancel 0 over 0 or infinity over infinity. It just doesn't work. So these aren't well-defined symbols that we can do arithmetic on of division and multiplication in this way. So we have to use other means, and that's where we're using L'Hopital's rule. So let's take a look at our promised example right here, 1 to infinity, going to e. So let's take a look at that. Okay, so for instance, we have the limit as x approaches 0 of 1 plus x and let's go from the right side, raised to the 1 over x. Okay, so it looks like the top is heading toward positive infinity. And this part right here is heading toward 1. So it's kind of the setup that we want. Okay, now let's go for it. All right, so when we do this and we apply a natural log, remember what's really happening. It's like we're taking e to the natural log of all this. And the reason why we do this is because we want to have the exact same limit as we had originally. And e and natural log undo each other. So this is the limit we're taking, but this limit can pop up inside the e right here. So we can really be thinking e to the limit as x approaches 0 from the right side of natural log of 1 plus x raised to the 1 over x. Okay, so we're going to take this limit. Now, this natural log allows us to bring that exponent down. So we have 1 over x times natural log 1 plus x. Now, notice we already have a fraction here, just because this was a fraction itself with the denominator. So we just have natural log 1 plus x all over x. And we need to take this limit as x approaches 0. Now the top, notice, will head toward 0, and the bottom will head towards 0, just as we were expecting. Okay, so we take a limit, or we take a derivative of the top, which is 1 over 1 plus x, and then times 1, because the derivative of 1 plus x is just 1, all over derivative of x, which is 1. So we took the derivative of the bottom, it's right here, derivative of the top, and it's right here. Now we take a limit as x approaches 0. And notice we can just plug in right now. We can just plug in 0. It's well defined. In fact, it's 1. But notice that what we just computed was this. This limit is 1. So the ultimate limit that we're after is e to the 1, which is e, which means that this limit right here is equal to e. Thanks for watching.